The Higher Education Research Institute at UCLA collected data from 302,458 incoming freshmen from 315 four-year colleges and universities in the United States. 72.2% of those students replied that they believe that same-sex couples should have the right to legal marital status. Suppose that Hannah randomly chooses 11 freshmen from among those who were surveyed. Hannah is interested in how many of the 11 freshmen believe that same-sex couples should have the right to legal marital status. Let the random variable x be the number of students out of the 11 freshmen that Hannah randomly chooses that believe that same-sex couples should have the right to legal marital status. How is x distributed? So we're going to start by looking at what distribution we're dealing with here. Now this is a binomial distribution, so we're going to go down here to the b. X is a binomial distribution. How do I know? Because we have a fixed number of trials. We have 11 trials. We're sampling 11 freshmen. Each one of those 11 freshmen might believe that same-sex couples should have the right to legal marital status, or they might not. Okay? So each one of these freshmen is its own trial. Now what about these values? This first value is the number of trials. There are 11 freshmen, there are 11 trials. And then this is the probability of success. In this case, Hannah is interested in how many of the 11 freshmen believe that same-sex couples should have the right to legal marital status. So a success is that the student believes that same-sex couples should have the right to legal marital status. And according to the problem, 72.2% of all students believe that they should. Okay? So 0.722, converting that percentage to a decimal. Okay? So this would be my n, and this is my p. All right. Now, let's find the probability that exactly 8 of the 11 freshmen sampled believe that same-sex couples should have the right to legal marital status. So this is where we're actually going to calculate a probability. And we're going to use that d-binom function. Okay? We're going to tell the value we're interested in. In this case, we care whether exactly 8 of the 11 freshmen believe that same-sex couples should have the right to legal marital status. So that's the first number. Then we provide the essential information about the binomial distribution, the number of trials and the probability of success. So size is the number of trials, in this case 11. The probability of success of any one trial is 0.722. So prob equals 0.722. And so the probability that exactly 8 of the 11 freshmen sampled believe this is 0.26176, or about 26%. There's about a 26% chance that exactly 8, so not 7, not 9, but exactly 8. Okay? Next question's a little trickier. It's similar though. Find the probability that at least 7 of the 11 freshmen sampled believe that same-sex couples should have the right to legal marital status. Okay? Well, what we don't want to do is just put 7 here. Okay? Now, the size stays the same number of trials. The probability stays the same, but this is giving us the probability that exactly 7 believe that same-sex couples should have the right to legal marital status. That's not what the question asking. It's saying at least 7. So it could be 7 or anything bigger, right? That's what at least means. So what we're going to do here is we're going to create a list of what the possibilities are, okay? So sometimes it's a little tricky to come up with the list. What does at least 7 mean? At least 7 of the 11. Well, I like to use it in a sentence. Is 7 at least 7? Yeah, 7 is at least 7. If I have 7 apples, and I have at least 7 apples, okay? What about 6? What if I go lower? Is 6 at least 7? No, 6 is less than 7, smaller, right? If I have 6 apples, then I don't have at least 7 apples. This is saying that the least amount would have to be 7. So I couldn't go lower than 7. What I can do is go higher. So 8 would be okay, for example, because if I have 8 apples, I have at least 7 apples. So 7, 8, and I'm going to keep going as far as I can because it's saying I can go bigger. The biggest number I can include in this list is 11 because that is the number of freshmen. I can't have more than 11 of the 11 freshmen say that they believe same-sex couples should have the right to legal marital status because that's the most number of freshmen that Hannah is surveying, right? You can't have more than there is. So this can never be bigger than your number of trials, okay? So what I'm going to do now is I'm going to use that same dbinom function, but instead of putting just the single value, I'm going to give it the list of values. The number of trials is the same. The probabilities of success is the same. But if any of these things happen, then I will have at least 7 of the freshmen sampled believe that same-sex couples should have the right to legal marital status. Okay, so what happens now? Now, notice I don't get a single value, but it gives me the list. Okay, this list represents the probability for each one of these possible outcomes. So the probability that 7 of the 11 believe this is 0.20. Probability that 8 of the 11 do is 0.26. Probability that 9 of the 11 do is 0.22, and so on. Okay? Now, these are mutually exclusive outcomes. If you have 7 of the 11, exactly 7 of the 11 freshmen say that they believe that same-sex couples should have the right to legal marital status, then you cannot possibly have 8 of the 11 say this, right? It could be exactly 7 or exactly 8, but it can't be both, right? Because these are mutually exclusive, we could find the total probability by adding these up. Remember that property about mutually exclusive in the word or, okay? Saying that at least 7 believe this is like saying that 7 or 8 or 9 or 10 or 11 do. And so what we're going to do is we're just going to add these probabilities up to find the total probability. So to do this, I just wrap it in this sum function. Sum says add everything up in the list, and I wrap it in between these parentheses. So that's what I want added up, okay? So if I click evaluate, that is the probability I'm getting. That is the probability that at least 7 of the 11 freshmen sampled believe that same-sex couples should have the right to legal marital status. Okay, just 2 more things. We want to find the mean and the standard deviation of the distribution. We're going to go back to the formulas we learned earlier. Okay, first I'm going to stick in what n and p is. N is 11, p is 0.722, which means my mean or my expected value is n times p. That's our formula for finding the expected value or the mean for a binomial distribution. And that's 7.942. So that's what we would expect to happen. We would expect 7.942 of the freshmen surveyed to say that same-sex couples should have the right to legal marital status. Now, of course, we can't get exactly 7.942, but this is kind of suggesting that maybe 8 is more likely than 7, right? It's kind of as in the middle as we can. And then standard deviation. That's n times p times 1 minus p, and then I take the square root of all that. Okay, that's, again, just using the formula that we learned for the standard deviation of a binomial distribution. And that is 1.485892. Submit all parts, and we have it.